Hi and welcome again. So in this video, basically I'm going to be showing you, or I'm going to be teaching you the notion of pointers. What is pointers? So pointers basically are some variables that instead of holding data, instead of holding numbers or text or whatever, they hold addresses of other variables. They hold addresses. Okay, so they hold basically a number, an integer number, which is an address of another variable. It could be of another variable, it could be an address of an array, it could be an address of a string, an address of text, an address of a struct. It could be an address of anything, really. But it's an address, it's just a container that contains an address. So in order to declare a pointer, the first thing you need to do is to type in the type of the variable that you want your pointer to point to. We just said that a pointer is a variable that has the address of another variable, right? So we have to know the type of that other variable that we have its address. If I say that a pointer has an address of another variable, that basically means that that pointer points to that variable, okay? If I say I have an array, a variable a that has the value 5, and I have a pointer p, and we say that p has the address of a, so p has the address of a, then basically that means that p points to a. Okay, that's the notion that I want you to remember here. So if you'd like to declare a pointer, you just type in the type of the variable that the pointer points to, and then star. That star there, asterisk there, means that p is just a pointer. It's not an integer, it's a pointer. A pointer that points on some variable of type integer. And here I say that p takes the address of a. Since p is a pointer, then we are interested about addresses. That's why p takes the address of a. Okay? Now if I, for example, want to print an integer, want to print p, the pointer p, I want to print it out. And I print, as you can see, there's a random number here. That's a random address. Okay? Since the p is a pointer, it has an address. That's a random address. The address of a. Okay? Now, if we want to see what value do we have at that exact address, in order to do that, all we need to do is to add a little asterisk in front of the pointer. So p is a pointer. When I try to print p, it'll print the address that p points to. But if I add the asterisk, then I'm going to print the value that p points to. Okay, not just the address, it's the value. And as you can see, it's 5. Because p points to the address of a, and the address of a contains the value 5. So if I try to print the value that p points to, then actually I'm printing the value 5. Okay? So that's the intuition that I'm trying to make here. You can access the content of a variable with other pointers that point to that variable. Now if I, for example, add a little asterisk there, p, and then I say that value will take 7, let's see what happens here. If I try to run the code, as you can see, now the pointer p has the value 7, right? Because we've changed that value that p points to. If I replace that asterisk p with a and I print again, as you can see, it's 7. Okay, so both of these, the a and the asterisk p, are actually talking about the same value. Okay, they're talking about the same values. If I change the content of A or I change the content of asterisk P, it's just like if I did the same thing, okay? Because both of them are talking about the same address, the same place in memory. If A changed that place, meaning that B will notice that that place has changed, and vice versa. Now, some quick facts here. If I declare an array, let's call it R, of size 10, it's exactly as if I have created a pointer called R. So these two writings are equivalent. So that one and this one. Well, they're not exactly equivalent, but they're almost equivalent. Okay? The only difference here is that when we declare a variable this way, we're actually allocating 10 integers of memory that we have the right to access and modify and do whatever we want to do with them. But if we just declare a pointer like this, then it's basically an array, but we are not able to access the 10 element or the 20 element or whatever, because we have not declared any elements yet. So in order to make them equivalent, all we have to do is to allocate 10 integers, okay? And to allocate 10 integers, there's a special magical function back again. So there's a special magical function called the malloc, the memory allocator. So the memory allocator is a function that takes the size, how many bytes you want to declare, and again we're gonna explain the notion of bytes and bits and later, but again this malloc takes how many byte you want to declare, and then it returns the address of where those bytes got reserved in memory. Okay, so it's kind of complicated, but it is not actually. The malloc asks the operating system, okay, oh operating system, I want to reserve for me, say for example 100 byte. Okay, we want 100 byte from you, oh operating system. That 100 byte, after the operating system reserves those bytes for you, this function will return the address. Where are those 100 bytes? So I'm going to give it 100, and then the malloc will return the array, will return the address, and we're going to store that address into the pointer array. And both of these two lines will behave the same, exactly the same. Well, not exactly, because 100 bytes will reserve for you 25 bytes. If you want them to be 25 integers, sorry. If you want them to be 10 integers, we're gonna give it 40, because every integer takes 4 bytes, and we're reserving 40 bytes. So 40 divided by 4, that gives us 10. So we have 10 integers. So we're reserving 10 integers and we're getting their address back. Okay? So if I try to print the R here, well, it tells me that I have declared the same variable twice. So that gives me the address of that. variable, the first variable. That gives me the address of the second variable. So there's also another difference between these two arrays here, is that the first one is constant, meaning that I cannot do something like this. I cannot say r++, okay, r++. I cannot like shift the array one step right or something. I cannot, while with pointers I can. So arrays are pointers, constant pointers. So if we'd like to just as I was talking, if you'd like to declare an array, dynamically, meaning with a malloc function, you have to give it its size, how many elements you want that array to contain. But it's bad practice to give it numbers like this. It's better if you give it like size of, and then you give it int, and then times how many numbers, how many elements you want. We want 10 elements. This way, this basically means that we don't care what is the size of an integer is, but whatever the size of that integer is, we want 10 of it, okay? We want 10 elements, 10 times the size of every byte. We want all of that allocated, and we take its address back and we put it in an array. And since array is an integer pointer, the last thing we have to do is to cast the elements. So it's an integer pointer, okay? Meaning that because this returns a void, and this is of type integer pointer, so you are assigning something that is void on something that is an integer pointer. They are not the same type, so you have to make them the same type. You add this little instruction here to force the right side of the equation to become the same type of the left side of the equation. So, even though this array is declared as pointer, I can deal with it as if it is an array. I can, for example, say like this, r. I can, for example, print r of 0, just like that. It'll print some number. Let's put in some number in it. So r of 0 takes 9. And if I print that r of 0, it'll print 9. Okay? This same way of writing this instruction, we could just write it differently. We could just write it like this. So r plus 0, this will return the address, and then we add a little asterisk there, and both of these are similar. Okay? So for every I positive integer, these two expressions are equivalent. You can use this one, the first one, or the second one. I personally do prefer using the first one because it's easier to understand, it's easier to work with, plus it's cross-platform, means that a lot of languages use the first expression only. Okay, so if you move to JavaScript or Java or C# or whatever, they do not use the notion of pointers. So there's no this star thing here. All of them use the first expression. So I do encourage you to only stick with the first expression unless you have to use the second one. Now, since pointer can be of type integers, or can point to double, or can point to strings or whatever, they also can point to structs. So you can, for example, create a struct. I'm gonna call it struct like node, for example, and then my struct is gonna have some values. So value 1, value 2, and so on. Then I'm going to use type def struct pointer. Struct node will be called node. And then basically I can create node pointer called n. See, so n points to an entire node. This is a node. N points to an entire struct. Okay, so it doesn't have to point at an integer or a string or a character, whatever. It can point to any type. All you have to do is to declare it the correct way, the right way. So if we recapitulate what we've been seeing here, if you want to declare a pointer, just give it the type and then an asterisk and then the name of the pointer. If you want to access the content that the pointer points to, you just add an asterisk before the pointer. So n here is just returns the address, but asterisk s returns the value that the address points to. If you want to print the address of any variable, say b, all you have to do is to add that ampersand before it. That will return the address of your variable. Now, if you use something like this, for example, n++, this will increment the address of n, right? It'll jump to the next node. So if node takes 8 bytes of memory, then when you use n++, actually you're incrementing the address by 8 bytes. Okay? So it depends on the type of the pointer. So this operator will not always add 1 to the address. It'll add the number, it'll add the size of that type that it points to. The same thing, the minus operator, okay? It will decrement by 1 node. If you subtract 2 pointers from each other, the result will be the difference between them, which is how many elements between them. Okay, so if we have, for example, node n, and we have another pointer node m, if we say n minus m, then that will return how many elements between n and m. I mean, how many ways, how many different iterations you have to do if you perform the n++ to reach m. How many times you have to execute this instruction in order to reach m. Of course, we're supposing that the address of m is bigger than, n++. We're supposing that the address of n is bigger than the address of m. Okay, otherwise it will never reach it. So I know that the notion of pointers is not pretty straightforward. It's a lot of students struggle from this notion, but you'll get the idea better when we start doing the exercises.